Our galactic neighborhood. A mere century ago, most astronomers believed that everything we could see in the night sky belonged to one galaxy, our own Milky Way. Yet, there were doubts. Some suspected that fuzzy patches of light known as nebulas were actually distant islands of stars, far beyond our galaxy. Still, no one knew for sure until 1923, when Edwin Hubble used the world's largest telescope, perched atop Mount Wilson in California, to measure the distance to the Great Andromeda Nebula, proving that it was much too far away to belong to our galaxy. The Andromeda Galaxy, as we know it today, is the Milky Way's biggest galactic neighbor. The Milky Way and Andromeda are actually the largest members of the local group, a collection of nearby galaxies bound together by gravity. These two companions are spiral galaxies, each sporting star-filled arms that wrap around a bright, dense core of older stars. And each is surrounded by a number of small, oddly shaped satellite galaxies known as irregular dwarf galaxies. Observations made with Hubble and other telescopes suggest that spiral galaxies such as the Milky Way and Andromeda grew as dwarf galaxies merged, and that they continue to grow larger even now by pulling in and absorbing these smaller galactic satellites. In fact, the Milky Way and Andromeda galaxies are on a collision course of their own, fated to crash into each other and unite into an even larger galaxy billions of years in the future. Computer simulations fed by Hubble observations of Andromeda's motion show that the dramatic encounter, predicted to begin 4 billion years from now, will be a head-on impact, flinging our Sun and its planets into a different part of the galaxy, and taking about 2 billion years to eventually settle into the much larger, oval-shaped, elliptical galaxy. Studying ancient stars in the Milky Way, conducting a cosmic archaeological dig at the center of our Milky Way galaxy, astronomers used Hubble to uncover a population of ancient white dwarfs, smoldering remnants of once vibrant stars that inhabited the core. The observations are the deepest, most detailed study of the galaxy's foundational structure, its vast central bulge, which lies in the middle of a pancake-shaped disk of stars where our solar system dwells. Finding these relics can yield clues to how our galaxy was built, long before our Earth and Sun formed. Hubble's observations support the idea that the Milky Way's bulge formed before its disk did, and that the bulge's stellar inhabitants were born in a relatively quick 2 billion years or less. The rest of the galaxy's sprawling disk of second- and third-generation stars grew more slowly in the suburbs, encircling the central bulge. The Hubble survey also found slightly more low-mass stars in the bulge compared to those in the galaxy's disk, suggesting that the star birth environment in the bulge was different than it was in the disk. Tracing the origin of an intergalactic cloud just beyond the edges of our galaxy, two nearby dwarf galaxies are engaged in a cosmic tug-of-war. These galaxies, the Large Magellanic Cloud and Small Magellanic Cloud, orbit our Milky Way and gravitationally pull on one another. As they do, over the past billion years or two, one of the galaxies has torn a huge cloud of gas out of the other, a structure that stretches half the length of our galaxy and connects the Magellanic Clouds to the Milky Way. This cloud is supplying fresh material to our galaxy, which feeds new star formation. Astronomers call it the leading arm, because it extends out ahead of the Magellanic Clouds in the direction of their motion. However, until recently, they did not know which of the two dwarf galaxies was responsible for pulling this gas from the other and from which galaxy the gas was coming. Astronomers used Hubble to study what the leading arm is made of to see whether it was more like the Small Magellanic Cloud or the Large Magellanic Cloud. They analyzed the light from 7 quasars, the bright cores of active galaxies billions of light years behind the leading arm. Hubble's cosmic origins spectrograph measured how much light was absorbed by different elements in the leading arm's gas. These measurements, combined with observations from the Green Bank Telescope Radio Observatory, suggested the gas in the leading arm came from the Small Magellanic Cloud, and that it was the Large Magellanic Cloud winning that gravitational tug-of-war. Surveying star clusters in the Andromeda Galaxy, a detailed Hubble survey of our largest galactic neighbor, the Andromeda Galaxy, allowed astronomers to make a surprising discovery. The percentages of massive stars and low-mass stars in Andromeda's star clusters are similar to what's found in our Milky Way. This suggests that the universe follows a formula when creating new stars, producing a consistent distribution of stellar types, from massive blue supergiants to small red dwarfs, every time. Astronomers did not expect the stellar mass ratio to be so similar in both galaxies, given the complex physics involved in star formation. This insight will help them better interpret the light from distant galaxies and understand how stars formed throughout the universe's history. The panchromatic Hubble Andromeda Treasury FAT program captured nearly 8,000 images of 117 million stars and 2,753 young, blue star clusters in the Andromeda Galaxy. Astronomers recruited the help of 30,000 citizen scientist volunteers who sifted through the thousands of Hubble images to search for these star clusters, which range in age from 4 million to 24 million years old. One specific finding from the analysis was that the most massive stars in the clusters are 25% less abundant than previously predicted. This implies that astronomers were underestimating the number of smaller stars forming alongside the massive stars, and thus underestimating the masses of distant star clusters and galaxies. The results also indicate that the early universe did not have as many heavy elements for making planets, because there were fewer supernovas from massive stars to produce those elements. Measuring a giant halo round the Andromeda Galaxy, analyzing 5 years' worth of archived Hubble observations, astronomers discovered that the immense halo of gas enveloping the Andromeda Galaxy is about 6 times larger and 1,000 times more massive than previously thought. The dark, nearly invisible halo stretches about 1 million light-years from its host galaxy, halfway to our own Milky Way galaxy. There is so much hot gas in this immense halo that its mass is half that of all the stars in the galaxy itself. If it could be viewed with the naked eye, the halo would be 100 times the diameter of the full moon in our sky. However, the gas in Andromeda's halo is dark, so astronomers used Hubble to study quasars, the bright cores of distant galaxies located behind Andromeda, to see how the quasar light was affected as it passed through the gas. By measuring how much a quasar's light is dimmed at certain wavelengths, astronomers could determine how much gas is in Andromeda's halo between us and the quasar. In addition to determining the size and mass of the halo, astronomers also determined that it is enriched in elements much heavier than hydrogen and helium, which only come from exploding stars called supernovas. These findings offer more insight about the evolution and structure of giant spiral galaxies, one of the most common types of galaxies in the universe.